imagine typing the words, "I can't believe you just said that."
Okay.
But then right next to it, you add a pair of brackets that just say, "Laugh sarcastically."
Oh, wow.
Yeah. You hit enter, and in literally 100 milliseconds, which is faster than a human being can even blink, your computer spits back this perfectly voiced, subtly aggressive, incredibly human laugh.
It's wild.
Right. We aren't talking about, like, some post-production trick in a sci-fi movie here. We're looking at an open-source AI model that is doing this right now.
Yeah, today.
Exactly. So welcome to the deep dive.
Yeah.
We are thrilled you could join us. Our mission today is to explore this fascinating system called Fish Audio S2. We really want to understand how the technology has evolved from, just stringing robotic syllables together.
To instantly grasping human emotion, pacing, and tone. It is a massive leap forward.
It really is.
What we are examining today is an AI that doesn't just mimic the superficial sound of a voice, it actually understands the semantic intent behind the words.
Okay, let's unpack this, because the sheer scale of the engineering here is just staggering. We were looking at their flagship model, S2 Pro.
Right, the big one.
Yeah. This is a 4 billion parameter model. And they didn't just train this on a handful of clean audiobooks, This system digested over 10 million hours of audio.
Across roughly 50 different languages, too?
Yeah, 10 million hours.
What's fascinating here is that the creators of Fish Audio S2 aren't positioning this as just like a fun experimental research project.
Right.
They have built an open source system that is openly claiming to be the best text-to-speech system available anywhere, period.
Wow.
Yeah, beating heavily funded closed source models from massive tech giants in some of the industry's most rigorous benchmarks.
And, big numbers, 4 billion parameters, 10 million hours. They're great for the spec sheet. But for you listening right now, the real magic is in the actual user experience.
Exactly.
It really comes down to this feature they call fine-grained inline control, which, honestly, it completely changes how you interact with generated audio.
It does, because if you look at legacy audio generation tools, the interface was it was highly mechanical. You were basically acting as an audio engineer.
Right. If you wanted the voice to sound like a little more excited, you had to deal with these clunky visual sliders.
Pushing buttons and dragging sliders.
Exactly. You're adjusting the pitch up by a few decibels, tweaking the speed percentage, or maybe dropping in these really complicated hard-coded code tags just to force a half-second pause.
It was exhausting.
It was. But S2 uses natural language tags typed directly into the text. You just use brackets. You type whisper in small voice, or professional broadcast tone, or pitch up.
And that represents a profound shift in the architecture. In older systems, tags were rigid and predefined.
How so?
Well, if you typed a tag for happy, the system was essentially just triggering a pre-programmed acoustic preset. It was a one-to-one mapping with no real understanding.
Just a canned response.
Right. But S2 accepts open-ended, free-form textual descriptions.
It feels much less like programming a machine and much more like, being a movie director giving notes to an actor on a soundstage.
Oh, that's a great way to put it,
You hand the script to your lead actor and say, okay, right here, give me a professional broadcast tone, but then in this next sentence, I want you to drop it down and whisper in a small voice. You are giving emotional direction word by word.
Which means the AI has to actually understand the semantic meaning of the phrase professional broadcast tone.
Right.
It grasps what that signifies in the context of human communication, and then it instantly maps that semantic understanding directly to an acoustic output.
So it knows what broadcast sounds like.
Yes. It knows that a broadcast tone requires a certain resonance, a specific cadence, clear enunciation, whereas a whisper requires, breathiness and lower amplitude.
But that is exactly where my brain gets stuck.
Why is that?
How does a machine translate a semantic concept, like a few words inside a bracket that say laugh, into actual believable human sound waves? Because laugh isn't a word with letters you can sound out.
No, it's not.
It's breath, it's vibration, it's this completely unique acoustic texture. How does a computer build a laugh from scratch?
Well, to answer that, we really have to look under the hood at the systems engine. The architecture driving S2 is called a Dual-Autoregressive, or Dual AR, setup.
Okay.
It uses a decoder-only transformer combined with an RVQ-based audio codec. And this codec runs at a 21 hertz frame rate with 10 distinct codebooks.
Okay, stop right there. I'm going to need you to translate some of that alphabet soup for me.
Fair enough.
Let's start with the RVQ-based audio codec and these code books. What are we actually looking at there?
Think of a codebook as a massive, highly organized dictionary of microscopic sound fragments. Instead of trying to process audio as one continuous, overwhelming wave of sound, an RVQ codec chops the audio up into tiny, discrete tokens.
Oh, kind of like how a large language model chops text into individual words or syllables.
Very much like that, yes.
So it's turning continuous sound into a language of distinct puzzle pieces.
Precisely. And it processes these puzzle pieces at 21 hertz. That means 21 times a second. It generates a frame of audio.
Okay, that makes sense.
But human speech is incredibly complex. You can't capture a voice with just one token per frame. So for every single frame, it uses 10 code books, 10 layers of detail.
Wow. Here's where it gets really interesting, though, because looking at this dual-stage setup, an analogy came to mind. The system splits the work into two distinct parts, the slow AR and the fast AR.
Yes, exactly.
Is it accurate to think of this like a composer in an orchestra?
Go on.
Like the slow AR, which contains the massive 4 billion parameter model, operates along the time axis. It is the composer. It predicts the primary semantic codebook. It is writing the main melody, figuring out the meaning, the emotion, and the flow of the sentence over time.
That is a brilliant way to visualize it, actually. The slow AR does all the heavy intellectual lifting. It decides what to say and the general intent behind it.
Right. And then you have the fast AR. This is a much smaller 400 million parameter model operating along the depth axis.
The orchestra.
Exactly. If the slow AR is the composer, the fast AR is the orchestra. It instantly takes that melody and fills in the remaining 9 residual code books for that specific fraction of a second.
Adding the layers.
Yeah, it adds the rich acoustic textures, the breathiness, the subtle pitch variations, the harmonies, all that fine-grained acoustic detail.
I love that analogy. And the asymmetric design of this dual system is just an engineering triumph.
Really? Why is that?
Well, if you tried to use the massive 4 billion parameter model to calculate every single breath and microscopic frequency change, the system would grind to a halt. It would take minutes to generate a single word.
Oh, because it's just too much data for the big brain to process all at once.
Yeah. Exactly. By keeping the semantic composer slow and deliberate, and the detailed acoustic orchestra incredibly fast and lightweight, they solve a major bottleneck.
That's so smart.
You get the deep, nuanced understanding of a massive AI paired with the blazing speed of a smaller acoustic generator.
It's an elegant solution. The big brain figures out the why and the what, and the smaller, faster system builds the physical sound waves in real time.
Right.
But, I mean, an engine, no matter how beautifully designed, doesn't just automatically know how to follow a director's notes. How did they train this AI actor to actually listen when you tell it to whisper?
That happens during the post-training alignment phase. They used a reinforcement learning method called Group Relative Policy Optimization, or GRPO.
GRPO, got it.
Essentially, they had to create a highly sophisticated reward signal to teach the AI what a good generation sounds like versus a bad one.
And this reward signal isn't just grading one thing, right?
No, it's grading several things at once.
Yeah. It's looking at semantic accuracy like, did it say the right words? It's looking at instruction adherence. Did it actually laugh when the bracket said laugh?
Right.
And it's also scoring acoustic preference and timbre similarity, meaning, does it actually sound like a pleasant, consistent human voice?
Exactly. It has to balance all of those competing priorities simultaneously.
Now, I have to push back on this a little bit.
Okay, sure.
Because there was a detail in the training process that seems, well, counterintuitive. The system uses the exact same models to filter and annotate the initial training data as it does to reward the AI during this reinforcement learning phase.
Yes, it does.
If the AI is essentially using its own internal logic to grade its own homework, doesn't that create a weird feedback loop? Aren't you just reinforcing its own hallucinations?
This raises an important question, and honestly, it is a common pitfall in machine learning.
Right.
But in this specific architecture, reusing those annotation models doesn't create an echo chamber. It actually solves a critical problem called distribution mismatch.
Distribution mismatch. How does that work?
Let's use an analogy. Imagine you spend years learning to speak a new language by listening to a specific teacher who has a very particular dialect and grading rubric. You master their exact style.
Okay, I'm with you.
But then, for your final exam, you are graded by a completely different teacher from a different region using a totally different set of standards. You are going to fail. Not because you don't know the language, but because the target shifted.
Ah, I see. That makes a lot of sense.
When AI models are trained on high-quality human audio, they establish a baseline of what sounds good. If you then introduce a totally new external model to grade the AI during the reinforcement phase, the AI gets confused.
Because the new grader wants something different.
Exactly. The new model might penalize a perfectly good laugh just because its internal parameters are slightly different. By using the same models for annotation and the reward signal, the system operates under one perfectly aligned, consistent rubric.
So the teacher grading the test is using the exact same standards the student used to study.
You got it.
That makes perfect sense. It's not compounding mistakes. It's locking in a consistent target, so the AI can focus purely on executing the instruction perfectly.
Exactly.
But even with that efficiency, when I hear about a dual autoregressive engine, 4 billion parameters, and complex reinforcement learning evaluating multiple acoustic layers simultaneously, it just sounds incredibly heavy.
It does sound like a lot.
Yeah. You would assume it takes a massive supercomputer like 10 minutes just to process a single paragraph.
You would assume that, yes. But the performance benchmarks completely shatter that expectation. And the secret to that speed lies in how the model is structured to serve the audio.
What do you mean by structured?
Because S2 treats audio as discrete tokens, just like text. It is structurally isomorphic to standard large language models.
Wait, meaning it's built the exact same way as the AI chatbots we use for writing code or drafting emails?
Exactly. And because it shares that structural DNA, Fish Audio was able to plug S2 directly into SGLang.
Which is what?
It's a highly optimized production-serving framework designed for text models. They essentially hijacked all the speed optimizations that the tech industry has spent years developing for text and applied them directly to audio generation.
Oh, wow. And that includes some incredibly dense technical optimizations, right? Like continuous batching and paged KV cache.
Yes, those are key.
Can we break those down for the listener? Because paged KV cache sounds like something out of a computer science textbook.
It really does. Let's simplify it. Imagine an AI generating a 5-minute conversation. In older systems, every time the AI generated a new sentence, it had to mentally reread and reprocess the entire 5 minutes of previous audio just to understand the context.
That sounds terribly inefficient.
It was. Paged KV cache essentially allows the AI to store its memory of the conversation in easily accessible pages. It keeps the reference books open on the desk so it doesn't have to run back to the library for every single new word.
I love that. And continuous batching.
Continuous batching means the GPU isn't waiting for one user's entire paragraph to finish generating before it starts helping the next user. It dynamically swaps requests in and out at the microscopic token level.
So no wasted time.
Exactly, keeping the hardware running at maximum efficiency at all times.
And the results of combining the dual engine with those LLM speed tricks are just wild. I mean, the raw speed numbers are staggering. On a single NVIDIA H200 GPU, the real-time factor is 0.195.
That's incredibly fast.
It is generating over 3,000 acoustic tokens a second.
And for the end user, the most critical metric is the time to first audio. When a user submits a prompt, S2 begins playing the generated audio in approximately 100 milliseconds.
100 milliseconds. That is literally faster than human reaction time.
It is.
For you listening, think about what that means.
Wow.
If you are interacting with an AI voice agent powered by this, the moment you finish speaking or hit enter on a text prompt, the audio responds instantaneously. There is no buffering wheel.
No awkward pauses.
Right. There is no awkward 3-second silence while the computer thinks. It is as immediate as talking to a person sitting across the table from you.
And crucially, that blistering speed does not come at the cost of accuracy. This is where S2's benchmark dominance really shines.
Let's talk about the benchmarks.
On the SEED TTS Evil benchmark, S2 achieves a word error rate of 0.54% for Chinese and 0.99% for English.
To put that into perspective for our listeners, a word error rate of less than 1% is virtually flawless. Human transcribers, professional humans listening to audio and typing it out, often have an error rate of around 4 or 5%.
Yep.
This AI is literally mispronouncing or skipping fewer words than you or I do in our daily casual conversations.
It is outperforming heavily backed closed-source giants. It beat Qwen 3 TTS, it beat Minimax Speech02.
Incredible.
And beyond just pronouncing words correctly, it dominates in the audio Turing Test, specifically the emergent TTS Evil. S2 achieved nearly an 82% overall win rate against competitors.
82%?
Yes, showing unparalleled strength in paralinguistics, the natural pacing of asking questions, and handling complex syntactic structures.
So it has really mastered the subtle, messy art of human speech. But knowing it has this speed and this accuracy, I want to pivot to the practical application.
Sure, let's do that.
Because humans rarely just read a single clean monologue in a vacuum. We converse, we interrupt, we talk in groups. How does S2 handle the messy reality of actual communication?
Wonderfully well, actually. The system includes native features designed specifically for complex interactions, starting with native multi-speaker generation.
So what does this all mean for a developer or a creator using the software? Let's say you want to generate a podcast intro with 3 different voices. In the past, you'd have to generate 3 separate audio files and stitch them together in editing software.
A total pain.
Right. But with S2, you can upload a single piece of reference audio that has multiple people talking. You don't have to painstakingly chop up the file.
Not at all.
S2 isolates every speaker's unique vocal features and assigns them a specific token, like speaker 1 or speaker 2. Then, in your text prompt, you just drop in those tokens to control who is talking. You can generate a multi-voice interaction in one single pass.
It completely removes the friction of audio engineering, but if we connect this to the bigger picture, the multi-turn generation feature is where this becomes truly transformative for conversational AI.
Like automated customer service or AI companions.
Exactly.
Walk us through how a multi-turn conversation actually works with this system.
Well, because S2 is built on that LLM-style architecture we discussed, complete with the paged KV cache, it has a significantly expanded context window.
Meaning it remembers more.
Yes. In older text-speech systems, every generated sentence was basically an island. If you told the AI to yell a sentence angrily, the very next sentence would instantly revert back to a calm, robotic default unless you specifically coded it to yell again. It had no memory of its own emotional state.
Oh, man. But with S2, if you were building an automated customer service agent, you don't want it to sound like it's blindly reading a script. If a customer gets frustrated and the conversation gets tense, S2 remembers that tension.
Exactly. It tracks the emotional arc.
If the AI apologizes, it remembers that apologetic, de-escalatory tone 5 minutes later in the conversation. It maintains logical and emotional consistency over a long period.
Right. It isn't just generating sound in a vacuum. It is reacting to the ongoing flow of a dialogue. And it can do all of this using any voice you want, thanks to its rapid voice cloning capabilities.
And this is the feature that really feels like we are living in the future.
It really does.
To accurately clone a voice, S2 only requires a short reference sample of between 10 and 30 seconds. 10 seconds.
It's unbelievable.
And because of that incredibly detailed dual AR engine, the composer and the orchestra working together, it captures not just the basic pitch of your voice, but your specific speaking style, your breath patterns, and your emotional tendencies.
All from 10 seconds.
And it requires 0 extra fine-tuning or coding from the user. You just upload a 10-second voice memo, and it can speak perfectly in your voice.
The efficiency of that is staggering. To extract a complete, robust acoustic fingerprint from such a minute amount of data is a testament to how deeply the 4 billion parameter model understands the underlying mechanics of human speech.
It really is. So let's look back at the journey we've taken today. We started by looking at an open-source GitHub repository for Fish Audio S2, and we uncovered an absolute powerhouse.
You really did.
We've seen how fine-grained inline control lets you act like a movie director, typing natural language directions right into the script. We break down the asymmetric dual AR engine, the semantic composer, and the acoustic orchestra.
Such a great analogy.
Thank you. We explored how it perfectly aligns its training using GRPO and how it hijacks LLM text optimizations to generate flawless audio in 100 milliseconds, shattering industry benchmarks along the way.
It is a profound technological achievement that officially leaves the era of robotic, glitchy computer voices in the dust. But as we look at what this technology enables, it leaves us with a rather profound question to consider.
What's that?
If all it takes is a 10 to 30-second audio clip to perfectly clone someone's voice, complete with their unique emotional cadence and breathing patterns, how will we determine what is real in the future?
Wow, yeah.
If a synthesized voice can instantly recall the emotional context of a conversation and dynamically react with a perfectly timed, sarcastic laugh better than we can on a bad day, does the very definition of what it means to sound human need to change entirely?
That is an incredible, slightly dizzying thought to leave on. The line between human and machine hasn't just been blurred, it might have been erased entirely. Thank you so much for joining us on this deep dive. We hope this exploration gave you some fascinating insights and a new perspective on the future of audio. Until next time, keep exploring and stay insanely curious.